So thank you for the introduction. I'm going to talk a little bit about the development of the IEEE P7009 standard. So coincidentally, I'm the secretary of the working group that's developing this standard, and of course it's under development. So I can't tell you everything that's in the draft, but I can provide an overview of the discussions that we've been having and the process for the standard development itself. So I'll begin by just providing a brief overview of the IEEE standards development process. And this is just a picture taken from the IEEE standards website. Basically, there are 6 stages. First of all, obviously, there's initiating the project, then getting together an appropriate working group, and then the standard is drafted, which is the stage that P7009 is at the moment. And then the standard is sent for ballot, and usually that comes back with significant amount of changes, and once those changes are made, the standard receives final approval, and then it's maintained going forward. So, as I said, it's under construction, so I can't tell you a whole lot about the actual content of the draft, and anything that I do say is not really does not necessarily reflect the opinions of the members of the working group as a whole or their position, but it's just an overview and my experience in this working group. So, because I can't present the content, but I can present actually a paper that we had. So I'm going to go through some of the slides for that. And if there are any questions at the end, I'm quite happy to answer them as best that I can. And this particular paper it describes an overview of the standard, its current status, various difficulties we were having, and things that have been resolved. So the co-authors on this are members of the working group for developing P7009. And I should probably mention as well, so P7009, although it's on fail safety, it's actually one of 13 standards in the P7000 series that the IEEE is developing. Some of those standards have been completed. As far as I know, P7001, which looks at transparency, is finished, it's available. Others are still, going through this 6-stage process. So these standards were proposed as part of this global initiative on ethics of autonomous and intelligent systems. I'm not going to read the mission statement to you, but it's there on the slide if you're curious. Basically, we don't want this. So we don't want the bad robots, we don't want dangerous robots, we don't want any of these things. I say robots, but I mean autonomous and intelligent systems more broadly even. And that's where the motivation for this comes from, to ensure that everyone involved in developing these systems prioritizes ethical considerations and that they are advanced for the benefit of humanity. So more information about that, there's a link on the slide there if you're interested. So this is part of this ethics certification program, and it's developing the certification of ethical properties. And these include, like I mentioned before, transparency, accountability, fairness, privacy, responsible governance, safety, and security. But interestingly, the IEEE has added fail safety to that list. So fail safety is now considered to be an ethical property of autonomous and intelligent systems. And that is, for me, I find that quite interesting. So in this talk, I'm just going to provide an overview of the P7009 standard so far. I'm going to discuss some of the challenges that the working group has faced and discussed and argued, and some of the things that are ongoing as well. So I'm also going to highlight 2 exemplar use cases to give you a flavor for the kind of systems that we're talking about when we mean autonomous intelligent systems, as well as the various sectors that they could be deployed in and how the standard could give some kind of guidance or support for regulation in those areas. Yes, so to begin, I'll introduce the standard. Of course, for any standard, it is important to determine whether or not there's actually a need for it. And the motivation for P7009 is kind of clear. So essentially, current standards have this idea that safety is engineered into a system. So it's sort of safety by design, and this is achieved by following certain guidelines and executing particular activities during the product lifecycle. For the autonomous and intelligent systems present a bit of a challenge to this usual approach because they have to respond and adapt to a dynamic environment, a potentially physical environment, so they aren't really quite as suited to these sorts of traditional assurance approaches. And basically from that we can deduce that the current standards are likely not appropriate for AIS, and ensuring their safety will require us to think a little bit more about it and develop new approaches. So the purpose of IEEE P7009 is to identify fail-safe methods that stop these autonomous intelligent systems from causing harm, a practical way to include them in the autonomous intelligence system, as well as a way to measure the performance of these mechanisms when they're being put forward and operational in the context of AIS. I7009 is targeted to be a foundational standard. It's domain and application agnostic, where some standards, I know there are specific standards, for example, in aerospace that are applied to aerospace systems. P7009 is intended to be quite general, and with whoever is using it is left with the, I suppose, responsibility of ensuring that what they do matches the domain and the application that they're interested in. And in this way, we're providing a framework for these developers to decide what is or isn't fail-safe for their particular domain or their application area.
Marie, I think you just muted your mic, or just got muted by.
Oh,
yeah,
sorry.
Perfect. No, it is.
Don't know what happened there. So I'll go back here, will I?
Yeah.
Okay, so the development of any standard is difficult, and many challenges are, of course, encountered throughout this process. So we have settled quite a few challenges, but there are some that are ongoing as well, which I'll talk about later. Of the settled challenges, we are opting to use descriptions rather than definitions to, in terms of answering the questions related to autonomy and fail safety. Defining these things is very difficult. Providing a definition that everyone agrees on is even more difficult. So we've opted for descriptions, but we do have still to answer the question of what is meant by autonomy, what is meant by fail safety, and whether we're considering the process, the product, or both. So I'm going to step through these one at a time so that we can get a flavor for what I mean. So as I said, we're going to avoid definitions wherever possible. Now, I'm a formal methods person, so this lack of formalization kind of has taken a little while for me to get used to, but I do think it's the way to go, because it allows the various terms in the standard to be characterized by descriptions without being prescriptive. So this will allow the adopters of the standard to employ the most suitable definition for their sector. And the descriptions in the standard typically reflect both experience as well as established practice within a given context or domain. If we had used definitions, we would have run into a problem. We would have run into the risk of potentially being ignored or not being adopted if the definitions that we had designed were not precisely aligned with, I suppose, the existing terminology in a given domain. In the way that we've done this here is we've placed the responsibility on the people that are adopting the standard, and in that way we reduce the risk of misinterpretation and potentially if there are any adverse outcomes as a result of that. So then what is autonomy? And I'm sure I could probably talk about this for an hour, but I won't. It's a very difficult thing to define, and for this standard it was an obvious stumbling block from the beginning. Broadly, we consider an AIS as making decisions without human intervention, and we have outlined some key characteristics to describe what it means that it's for a system to be autonomous. It should have the capacity to make decisions without human validation. It should be able to act on those decisions while it's interacting with the real world or the physical world, and it should adapt and modify its decision-making process as well as the interactions that it has by learning. The take-home message here is basically that autonomy is in the eye of the beholder. As a result, we treat autonomy as a continuum, and we place the same requirements on both autonomous and semi-autonomous systems. You probably noticed that the standard in its name is for autonomous and semi-autonomous systems, and we don't differentiate between those things, or we don't, aspire to match any kind of level of autonomy. If the developer considers the system to be autonomous, then absolutely the standard can be applied. I hope that makes sense. But yeah, again, as I said, I'm happy to answer questions at the end. We're also quite agnostic in terms of the tech used to achieve autonomy. And I know I've said the process of learning up there, but there are other ways that autonomy is achieved that are not machine learning, such as more agent-based approaches and things like that. So this can be applied in all of those scenarios. Of course, then we have to define what is fail safety. And for fail safety, we have the description that we have agreed upon is that the system should be able to achieve a known state to prevent, mitigate, or to prevent harm, mitigate harm, and it should be able to do that in a deterministic way. This should be done automatically, either automatically in response to a failure or through some sort of external demand driven by a hazardous event or potentially a series of hazardous events. Now, of course, we're not pretending we don't see what's happening in the real world. We know that absolute safety can't be achieved. Accidents, of course, will happen. But what we're trying to achieve with P7009 is that the design and development process must ensure that the system can sustain faults and fail safety while continuing to provide an acceptable safe level of operation. Then when it comes to the challenge of products, process, or both, we're adopting a requirements-driven approach. We're defining a set of mandatory key requirements that span both the process and the product. And that in that way, we get this link between these things. The standard divide is those key requirements are complemented by a set of what we've termed critical properties, and we've defined a mapping between the key requirements and the critical properties. So I suppose the interesting part about this, and this is more general as well for certain types of autonomous systems, we're trying to separate various components. So we're separating the fail-safe elements from all of the functionality, and this standard specifically focuses on the fail-safe components of the system. So those are some of the challenges that we've argued enough, we're done, we're settled. But of course, as can be expected in this process, there are still more challenges, and they include things like verification, whether or not we can achieve fail safety by design, and the idea of autonomous fail safety. I suppose that might be a bit futuristic for now, but it's important that the standard can be, used for a long period of time and easily updated to as technology gets even better. So verification basically involves checking that the system meets the specification so that it does what it says it should do. For P7009, in the standard, we'll provide examples, but we will not restrict users to permissible verification approaches. In certain sectors, that's left to the sort of assurance case development process anyway. But the idea here is to not be too prescriptive so that we will rule out verification approaches that will be useful later. We have a verification subgroup that have been discussing things like what actually do we verify, what are the properties that should be verified, what is different about fail safety for autonomous systems, and what are the benefits and drawbacks of the techniques that might be used. So this particular verification subgroup has actually done a brief analysis of various verification techniques, and they've provided, I suppose, a lot of guidance to the main working group on this topic, and hopefully that will be integrated into the standard as well. So as software gets more complex, more fun, whatever way you want to look at it, but it's rarely monolithic for these autonomous and intelligent systems. this is really obvious in the robotics domain. Like if you have an autonomous robot, it's usually developed using a middleware like the robot operating system. And in that case, there are various behaviors or various functionalities are encapsulated into different modules. And this in turn, although it creates it quite modular and easy to kind of understand, easy might be too generous there, but a more straightforwardly understood system, the architectures themselves can be quite complex and often heterogeneous. They might use more than one programming language, various libraries, which means, of course, that we need these modular and heterogeneous architectures to be able to support fail safety through architectural design. And the way that we do that, as I kind of alluded to previously, is we're talking about extracting the fail-safe aspects and capturing them in particular components that we can do some analysis of. And then there's this fun idea of autonomous fail safety. So if we think about, okay, so if we look at this figure here and we think about autonomous vehicles driving along a motorway at speed, if, say, one car, maybe the middle car, experiences some error, it needs to be able to react to that. So it needs to do something, but obviously it can't just stop because there's another vehicle behind it, and if it stops, it's going to cause a crash. So you can potentially see the situation where this stop procedure is not always safe. So what this car should actually do, maybe in this situation, is autonomously navigate into the hard shoulder. So to do that, you can see now we're not just failing safety, we actually have some autonomous behavior in the fail-safe components. And that is something that's under discussion currently by the working group. How do we discuss these things? How do we actually verify these things? And when do we need the autonomy in the fail-safe components? We have been discussing various things, but one thing that has been particularly useful in this throughout this process is using sort of exemplar use cases or examples from industry, from academia, from various places to be able to essentially kind of test the standard or the draft standard, to be able to examine whether or not what we're saying is applicable in these areas and what the sorts of problems are that we face. So I'm going to talk about two particular use cases. The first one is in a tightly regulated environment. So if we imagine some tightly regulated sector, and these autonomous systems are evolving quite quick, and the issue that these tightly regulated sectors have is that they're often not able to certify them because the standards that they have or the processes that they have don't cater for autonomous systems yet. So we're hoping that 7009 can be useful in these domains. So one example would be a robotic arm for nuclear decommissioning. So you can see here is a figure of what happens. Basically, this piece of nuclear waste comes in, robot arms have to work together to decommission it. So one arm is holding it, you can see there's a clamp there, and then one of these other ones, this one here, is cutting it. Once it's open, then this guy over here has to come in and grab some certain stuff, put it, kind of sort it out, and pack it off again. So you can see that this particular system is really useful for nuclear decommissioning because it takes humans out of the equation. If humans were to try and unpack this waste, they would be, the consequences could be really bad. So autonomous systems in this sector, in this example, are not only useful, they're almost necessary, in my opinion. And they're really safety critical because if you potentially incorrectly target or, do the wrong cut, you could damage the operating area, you could cause a radiation leak. So there's a lot of safeguards that have to be included here in this kind of a system. And nuclear regulators, particularly the ones in the UK, for example, require a safety case to certify that the system operates safely. But as I said, they don't seem to completely understand yet how this can be done for AIS, although work on that topic itself is ongoing. Our opinion with P7009, or my opinion with P7009, is that it can provide these regulators that don't have this AIS into their in the usual process for regulation or certification. It can provide them with the guidance for incorporating these systems via the provision of effective, safe, fail-safe functionalities. So that was a tightly regulated environment. Now let's imagine something a little bit more loose. So there are many sectors that are at the moment unregulated or loosely regulated, where autonomous intelligent systems can provide a lot of help to taking humans out of equations, but they can also provide performance, I suppose, improvements. And if we envision one of these sectors, we have to imagine a place where current guidelines just don't cater for AIS, but actually they're just guidelines. They don't even have necessarily a tightly regulated process. So if we consider space, okay, space is the final frontier, as they say. The space sector is notoriously unregulated. There are certain, okay, so if you want to launch something with ESA or NASA, you have to meet their requirements. So there is some sort of an oversight there. But there are all of these private companies springing up that don't have to abide by those rules, and that don't. So you can launch your dangerous, potentially your dangerous thing somewhere else. So it does create an interesting area for autonomous systems, but it also creates an interesting area for this sort of certification, regulation, standardization process. So the example that we've been using in the working group for this kind of use case is autonomous satellite docking. So basically these two satellites are trying to dock. So it could be for refueling, it could be for debris capturing, or it could be for data collection, but they have to essentially come together without crashing into each other and dock. So yeah, as I mentioned, space is a new commercial enterprise, and satellites, of course, these things can be launched without approval from the agencies. But the crucial part here is that these systems are all mission critical. So a small software failure can lead to complete mission failure. There are large amounts of money involved in these systems, and yeah, you really don't want them to fail. So there is a need for I suppose, a very robust development process, robust verification process, and compliance with standards. And in this particular area, in an unregulated domain, the objective here for P7009 is to provide guidance for developers about how to ensure the fail safety of their systems. And that is, I suppose, there's two aspects to that. One of them is to be able to, for the company themselves that are making the system, that they know that what they're making is of high quality, so they can use 7009 for that. But also in these sorts of evolving domains or sectors that they don't have standards, but they don't have standards yet, right? So they might want to have them later. They probably will. And for these kinds of places, 7009 can be really useful. So I know I haven't taken too long. I don't want to say too much. I'm happy to answer questions at the end. So I'll begin by just concluding briefly. We have the development of the P7009 standard is ongoing, and we're using scenarios, use cases, and test cases to develop the standard and to be able to, I suppose, sanity check that what we're doing is the correct thing to do. We've a few subgroups. One of them is on verification, and they've done quite a bit of work on comparing various approaches and figuring out how these things can actually be used. Our focus is always on ensuring that the standard is both useful and usable. From I suppose more an industry perspective, that it's not something almost impenetrable or something that places too heavy a burden on the users of the standards. And if anyone would like to read the paper, the paper that we have here was presented at the International Symposium on Software Reliability Engineering, the industry track last year. So it's available online. I'm happy to answer any questions.